There are other solutions for the critical section problem that requires help from the hardware. That means the machine code itself has to be designed in a way that will not allow the cause of the problem to happen. That is being interrupted in the middle of changing a variable value. The basic concept is creating locks where when the process is actually changing a value of a common variable or a common data entity that is shared between processes, it will lock this data entity until it finishes the whole process of changing the value of this data entity. If we have a single process, we can simply disable interrupts. We will not allow an interrupt to happen to a process while it's running in its critical section. So this part of the process will be executed without preemption. In a single process environment, this will work, despite from a security point of view, this is not advisable because one process might disable the interrupts in the system and never enable it again. You have to restart the whole system and everything will be a huge mess. But what if we have multiple processes? Multiple processors, multiple CPUs? This will be completely inefficient. You cannot disable all interrupts across the multiple CPUs. And if the other processes running on different CPUs might be able to run their critical section simultaneously. So the disabling interrupts is not actually a good solution in either cases. Anyhow, modern operating systems, modern machines provide what we call atomic commands. Atomic, that means it despite it is actually multiple commands in machine code, it will be addressed as one single command and it will not be interrupted until all the series of these commands are executed. We will consider two of these atomic commands in the following minutes. One is test and set, the other is swap and test and swap. Okay, so we have two different commands that we shall see now. The concept is using a lock. This lock will be the lock will be used using an atomic command. Simply, you will acquire the lock, run your critical section, and then release the lock. That looks very simple. But the locking process itself, it can create a race condition. Which process can get the lock? That's why we need atomic commands. With test and set, it's very simple. You will test the value of the lock. If no other process has actually locked the critical section, Then you will lock the critical section, execute your critical section, and then unlock it. The most important thing in this, that is this command is executed atomically. It cannot be interrupted. So using this will make things very simple. The process that wants to enter its critical section will use test and set to see if the lock is not set. It will set the lock to true, executes its critical section, then reset the lock to false. The lock initially is false, it's not locked. If the lock value is true, then the process will do nothing. It will wait until the value of the lock is false. Simple and efficient, but it needs the help of the hardware for executing these commands in an atomic manner. Where compare and swap instruction is a little bit different. It will actually compare the value. It will compare the value of lock. If the value of lock equals the original value, it equals what it's expected, which is false, is fine. Otherwise, if it's it will compare the value of lock. It will expect the lock to be locked. If it's not locked, it will lock it, run the critical section, and then unlock it. As we shall see here. If the value of lock is not 0, that's what is expected. It's not 0. Someone is in their critical section. I will do nothing. If the value of lock is 0, then I will change it to 1 and execute my critical section and then reset the lock to 0. These two solutions are very simple and very straightforward. If you want to use test and set lock to solve our consumer producer problem earlier, to guarantee consistency with the value of the counter, what shall we see? Simply, a process will be waiting until its turn. If it's my turn, I will acquire a key to lock the critical section. I will run my critical section, then I will unlock the critical section. So I will examine, I will test. If it's my turn and the key is free, then I will set the key from 0 to 1, run my critical section, then reset, which is increasing or decreasing the value of counter. Then I will unlock counter and declare my lack of interest. That means I will change the value of lock. It's not locked anymore and it's not my turn. I'm not waiting. So anyone who is interested can come and execute. The rest of the chapter were mutex locks, semaphores, and the classic problems of synchronization and synchronization examples will be reading assignment, the first two sections might be included in your exams. The other two sections might be a subject of some written assignment that cannot be included in your exams. Thank you.